Hello physics students, this is Dr. Brenzi here. This is the lesson 2.1.4 video, and our objective here is that we will be able to apply Newton's third law to calculate forces on two separate bodies. Newton's third law of motion states for every action there is an equal and opposite reaction. And what Sir Isaac Newton meant by this is that for every force there is an equal and opposite force. So an example might be a couple of football players who are on a line of scrimmage, and when the play gets started, one of them is blocking on offense and the other guy is on defense trying to avoid getting blocked, and they collide and they actually exert a force on each other. So the white player is exerting a force on the green player, and the green player is exerting an equal and opposite force on the white player. So if we were to draw force-body diagrams for these two players, these two bodies, the white player would have a force exerted on him by the green player, which we might label F green. And then we draw a separate force-body diagram for the green player and have a force exerted on him due to the white player. And what Newton's third law states is that the force on the white player due to the green player is equal to the opposite of the force of the white player on the green player. So F of green on white equals negative F of white on green. Another consequence of Newton's third law of motion is that forces always come in pairs. And so, like if you're pushing a wall is pushing on you. If you were standing on ground, that ground is pushing on you. And believe it or not, you might think this is crazy, but if gravity is pulling you toward the center of the earth, then your body is actually pulling the center of the earth toward you. You might think, no way. Well, it's actually true. It's just that the mass of the earth is so massive, much more compared to you, that it actually experiences very, very little acceleration due to you, whereas you, on the other hand, experience negative 9.8 meters per second squared toward the center of the earth. So even though the accelerations are greatly different, the forces are exactly the same. One of the common misconceptions of Newton's third law is that some people think that these two forces, equal and opposite forces, are acting on the same body, and that's simply not true. That's incorrect. Newton's third law requires two bodies to exchange forces. So the correct way to draw this as a force-body diagram is to actually have two separate bodies and one force acting on one body, the opposite, equal and opposite force acting on the other body. So if you're going to invoke Newton's third law, make sure that you're not applying both of those forces to the same body. Now you might be saying, Dr. Brenzi, wait a minute. I know from personal experience that when these two guys get together and they are blocking one another, or one of them is blocking the other, that it's very seldom that both of them are actually go flying in opposite directions. And you are correct, but this force-body diagram is incomplete. What's happening here is that this white player is also exerting a force on the ground with his feet. And that force is propelling him in the positive direction. So we could say that this is F friction. Okay. And this white football player definitely wants to try to balance out that friction force with the force that green is exerting on him so that he doesn't get pushed back. And the green player is trying to do the same thing. He also has a friction force that he's exerting on the ground due to his feet going in this direction, so he also has a friction force. Okay, that is that is pushing him in the negative direction. So both of these guys actually have friction forces due to their feet that are acting in the opposite direction, so that neither of them gets accelerates, in a direction they don't want to go. Like the white player doesn't want to accelerate to the left, otherwise he's going to get beat. And likewise, the green player doesn't want to get accelerated in the right direction, otherwise he's going to get beat. So, but for the purposes of Newton's third law, this is a pair of forces right here due to the interaction between the green and the white player, and they are acting on the two separate bodies. One is acting on the white player, the equal and opposite force is acting on the green player. So for the purposes of Newton's third law, we have to think that these two separate forces are on two separate bodies. Okay? So let's go through a quick example here. Oh, actually, before I say that, I should also tell you that inanimate objects can also exert a force on animate objects. So let's say a bird is flying through the air, and this bird is flapping its wings, and as it flaps its wings, it exerts a force on the air that pushes it downward. But due to Newton's third law of motion, that air underneath its wings exerts an equal and opposite force, propelling the bird, or pushing the bird in the upward direction, and that's how birds fly. They're actually pushing against air so that they can experience a reaction force in the opposite direction. So, go ahead and write this example down, and when you're done writing this example down, you can unpause the video and join me. So the example is this. Let's say that there's a person, Kent, and he attaches a rope to a wall and pulls the rope with a force of 500 newtons. He later attaches this rope to a cart and pulls with a force of 500 newtons again. And the question is this: which object exerts a greater force on Kent while he's pulling? Is it the wall or the cart? So, let's quickly draw this out. Let's have a wall here. That's not a very good looking wall. And then there's a rope, and then there's Kent here pulling on the rope. And Kent is pulling on the wall with a force of 500 newtons. Well, what's the force that the wall exerts on Kent in this direction? It is equal and opposite, so it also has to be 500 newtons. Alright, now let's take a little cart. I don't know what carts really look like, but let's say that's a cart. And let's attach it to Kent with a rope. And again, Kent is pulling on the cart with 500 newtons of force. What is the amount of force that the cart is pulling on Kent? Well, it also is 500 newtons. Okay, those forces that have to be the same. The force that the wall exerts on Kent is 500 newtons, and the force that the cart exerts on Kent is also 500 newtons. Okay. Now, remember, going back to Newton's first law, which one is going to accelerate more? Well, if the mass of this cart is a lot less than the mass of this wall, this cart is going to experience a lot more acceleration than this wall will. And that's due to inertia. The mass determines acceleration. So, mass doesn't determine how much force is exerted from Newton's third law, but it does determine the amount of acceleration that the cart and Kent experience. So in this example, even if this were a much smaller mass than the wall, Kent and the cart would experience a lot more acceleration. However, in this case, where the wall is very massive, Kent wouldn't experience a lot of acceleration. He would just end up pulling on the wall and probably staying pretty stationary. Whereas here, he would start to experience an acceleration in this direction. Alright, that's it for Newton's third law, and we'll get an opportunity to practice this in class, and I look forward to seeing you soon. Bye.